Afternoon, everyone. So as you heard, this talk is on 100 gigabit per second Ethernet, which is quite a hot topic in the industry, as you can tell, because all the chairs are taken up by people sitting and people standing at the back, so it's a very hot topic. And so it's tempting in this type of presentation to start talking about products, but that's not very polite to talk about products in a conference, so I'm going to be concentrating on technology, and there'll just be one quick photograph of a product just to show you what a CFP module looks like, but in the main I'll be concentrating on technology because it is a technical conference, of course. So in terms of the talk, I'll give a bit of introduction about the trends in terms of capacity, how people deploy capacity between main cities in service provider networks. And then I'll talk about the 100 gig E technology itself. And at first, I'll talk about how 100 gig E works over short distances. So these are distance formats defined by the IEEE, and they've defined formats for carrying it over 10 kilometers and also 40 kilometers, and also some shorter distances. And then I'll talk about how to carry 100 gigabit per second signals through long-distance DWDM systems. And in both of those contexts, whether it's short distance or long distance, the way it's being done is quite different to the way signals are carried at, say, 10 gigs or 1 gigs. At 1 gig and 10 gigs, we're used to the fact that people just carry it as a bit serial data stream, nice and simple. Once you get to 100 gigs, you need to do something special, so I'll be talking about that. So here's a graph showing the trends in terms of inter-pop capacity in the largest networks. So this is showing the sort of extreme end of the spectrum as a function of time. If you consider 1998, that's when we first launched our first ever product, a core router, and that had interfaces which have speeds up to STM16 or 2.5 gigs. And that type of speed was regarded as very futuristic in those days, because most networks were using STM1 or DS3 on their main intercity routes. So STM16 was regarded as very large. Now, only 2 years later, that was followed by the first 10 gigabit per second router interfaces, and that was, of course, fueled by the internet boom and the optics boom. So in the space of 2 years, there's already demand for 10 gigabit per second interfaces. If we look now in the present day, we're in the situation where on busy intercity routes, people are now using multiple 10 gig E interfaces. And one example on the MPLS World Congress last year is that one service provider in his talk said that between some of his main cities, he's using 20 or 24 parallel 10 gigabit per second interfaces in order to achieve the capacity he needs. Obviously, using lots of parallel links like that is more complicated. You have to think about load balancing and lag and things like that. So obviously, it'd be much more convenient to have fewer fatter pipes in the shape of 100 gig Ethernet. So that's really a very big driver behind the 100 gig technology. And I'm sure you've seen all of the quotations in the media, people saying in the public domain, we're trying to get into the backbone space as quickly as possible with 100 gig Ethernet and so on. So certainly we're sensing a lot of demand for this technology. So from the point of view of Juniper, we've always been in very strong support of the 100 gig Ethernet from day one. And so what happened in the industry is about 4 years ago in the IEEE, a study group was set up called High Speed Study Group. This was in about 2006, in order to work out if there was feasibility of 100 gig Ethernet, was it technically feasible, and also was there market demand. And of course they concluded that there was. During those meetings, there was a lot of controversy about whether the IEEE should also work on 40 gigabit per second Ethernet, because there's a lot of demand from the sort of server industry and the storage industry. And the reason for that is that even for a high-end server, 100 gig Ethernet today would be regarded as overkill, and so it's regarded as sensible to have something in between in the shape of 40 gig Ethernet. And so what happened in the end is that the IEEE decided to work on both, and so they've been defining definitions for both 40 and 100 gig Ethernet. So in terms of what the IEEE is doing, they've made definitions for so-called grey interfaces. So what these mean are relatively short distance interfaces just for back-to-back connections, distances up to 40 kilometers, and various smaller distances as well, which I'll show you later on. The other aspect is how to carry it over DWDM systems, and the Optical and Internetworking Forum has been looking at that to some degree, and we've been involved in that aspect as well. So this slide shows some of the use cases for the IEEE grey interfaces. So obviously the first use case is just back-to-back connections between routers. So these could be in the same POP or could be in the same city in two different POPs interconnected over dark fibre, and so you can use one of these IEEE interfaces for that. The other use case is for hooking up to a long-distance DWDM system, and in that case you would need to have a transponder on the DWDM system. So what you've got from the router to the transponder is this IEEE grey interface, and so that's present on the router and on the client side of this transponder. And then what the transponder is doing optical to electrical conversion. So it's converting this optical signal coming in back to an electrical signal, which is then used to modulate a long-distance laser, and the signal from that is transported, potentially over thousands of kilometers through the DWDM system. And then on the other side, you've got a transponder as well, converts it back to an electronic signal, and then back into one of these IEEE short distance grey interface formats. So those are the two use cases when using these grey interfaces. Now, how the signal is carried within the DWDM part of the system is basically up to the DWDM vendor, because this is happening on the line side of the transponder, and so that's decoupled from what the router is doing. The DWDM vendor can do whatever they like between these 2 points, and that's decoupled from what the router's doing, because you've got electronic conversion here acting as a sort of demarcation point, if you like. And I'll talk more later about the details of how one can actually carry this signal through the DWDM system, because that's quite an interesting topic. Now, one interesting point when we get to 100 gigs is actually how to, create the signal and carry it through the optical fibre. Now, if you look at how optical communications work, the traditional approach, for example, at 10 gigs or at 1 gig or STM1 or something like that, is to use what's known as on-off keying. So the way that works is if you need to transmit a binary 1, you turn the laser on, and if you need to transmit a 0, you turn the laser off. And so it's literally like flashing a torch on and off to signify whether you're sending 1s or 0s. Now, if you're accustomed to things like radio communication or microwave communication or satellite communication, you'll probably think this is incredibly primitive, because in radio communication systems, they've been using higher order modulation schemes where you're carrying multiple bits per symbol. And so this concept of just carrying bits by, just flashing the light on and off would seem, very primitive. The difference is that optics have only been around for 20 or 30 years in terms of optical fibers, whereas radio has been around for, 100 years. So there's been more time to develop, fancier modulation formats in the radio domain. Also, of course, this is at much higher speeds. We're talking about speeds of 10 gigs and so on. Now, the thing is, if you tried to do this same sort of scheme at 100 gigabits per second, just transmitting the data serially using on-off keying, you would have severe problems, because these bits would only be 10 picoseconds apart. So it'd be really difficult to find a modulator that would operate within the transmitter that can do a transition between a 1 and a 0 in less than 10 picoseconds. You just can't buy modulators like that, really. The other aspect is on the receiver. How can you find a receiver of sufficient bandwidth that it can actually tell the difference between a 0 and a 1 when they're so close together? What will tend to happen is that the 1s would turn to merge into the 0s, and you'd have trouble to distinguish between them. The other aspect is propagation. How do you actually propagate this through the optical fibre? Because of impairments that the fibre imparts on the signal, which I'll talk about later. So all of these things put together make it very challenging to actually transmit data at 100 gigabits per second in a bit serial fashion using this on-off keying scheme. It is physically possible, and I'll show you an oscilloscope trace that shows that. So this is an oscilloscope trace showing data actually transmitted in bit serial form at 100 gigabits per second. So this scale is 10 picoseconds per division between these two lines, but it's really tough to do. It's very complex and very expensive. So in terms of commercial feasibility, it's not actually feasible to do something like this in terms of actual 100 gig products. So for that reason, what the industry has done is to do the concept of multiple lanes, at least for the IEEE grey interface format. So rather than trying to send the data bit serial fashion, it's actually striped over multiple lanes. And I'll show you a chart which illustrates that. So these are the formats that have been defined by the IEEE for transmitting 40 and 100 gig data over these grey interfaces. And so what you've got is various distance definitions and different types of fibre that you're carrying it over. So, for example, one definition is 100 G-base SR10. And so the SR stands for short reach, and the 10 means there are 10 lanes. And these lanes are actually 10 separate optical fibres in a ribbon cable, and so each one is carrying data at 10 gigabits per second. And so each Ethernet frame is actually striped across those 10 lanes. That's the way it's working. And this definition applies to multimode fibre over distances of up to 100 meters. So this is quite short reach, of course. Now the thing is, most sort of ISPs and service providers, they don't actually like having ribbon cable inside the POPs because it's a sort of non-standard cable. It causes problems with patch panels and things like that. What people really prefer is just using standard fibre pairs, just normal cables that you normally have within POPs. And so that's why the LR4 and ER4 specifications are much more popular. And so in both of these specifications, what you've got is 4 lanes, and this time the 4 lanes are actually 4 wavelengths sharing the same fibre. So this is sort of coarse WDM, and I'll show you a chart later showing the wavelength definitions for that. And so what you've got is LR4, which is a 10 kilometre definition, and you've got ER4, which is a 40 kilometre definition, using this coarse WDM scheme. And this is showing how that works in terms of the optical spectrum. So this is down in the 1300 nanometer band, and it's coarse WDM because these wavelengths are quite far apart. They're about 4.5 nanometers apart. And as I said, each one's carrying data at about 25 gigabits per second, and that's how you get the 100 gigabit Ethernet in total. So that's quite a pragmatic scheme to use, to achieve the 100 gig propagation. Now, one frequently asked question that comes up is people say, okay, so if I'm using this LR4 or ER4 formats where we're using these 4 wavelengths, does it mean that if I want to transport this over a DWDM system over long distances, my DWDM system also needs to carry that as 4 wavelengths each at 25 gigs? And the answer is very much no, because the assumption is that this LR4 or ER4 would be plugged into a transponder on the DWDM system, and then the transponder is doing conversion into an electrical signal and using that to modulate a long-distance laser. And so what it does on the long-distance side is decoupled from what's happening on the client side, and so it can do whatever it wants. It could send it over 1 wavelength, for example, which I'll show you later, or 10 wavelengths, or whatever it wants to do, because it's converted the signal to electronics as an intermediate stage. The other thing is you can't expect to directly inject this LR4 or ER4 signal directly into a DWDM system because it's in the wrong wave band. It's in the 1300 nanometer wave band. The spacing is not suitable, the spectral characteristics are wrong. So this LR4 and ER4, just to emphasize, are strictly for 10 kilometers and 40 kilometers, not for going directly into a DWDM system without having a transponder. Now the other aspect related to 100 gigs is pluggable optics. So as you know, things like 10 gigs Zenpacks and XFP pluggable optics have been very popular because you just need one sort of line card and then you can plug different optics into it according to what distance you need. And so by analogy, at 100 gigs, a new pluggable optic format has been defined, which is known as CFP. And the reason why it's called CFP is that C is the Roman number for 100s. That's why they called it CFP. And so what happened is that a consortium of optics vendors got together and defined how this CFP works. So you've got interoperability. You can have pluggable optics from various component vendors and plug them into the line cards. And so schematically, among other things, what they've defined is what's this data bus like that goes between the router interface and the CFP module itself, in terms of how many lanes have you got here and how the clocking works and things like that. And I'll show you a more detailed diagram. So this is taken from the CFP specs. And so on this pluggable module, which is shown in blue, you've actually got a lot happening. There's a lot happening on this quite small pluggable module. Because what you've got is, first of all, you've got 4 lasers, because this is assuming this is LR4 or ER4 specifications. You've got 4 lasers, each running at 25 gigabits per second. Then you've got a multiplexer to combine them onto one optical fiber. In the reverse direction, when the light comes in, you've got a demultiplexer. Then you need 4 separate receivers to receive each of those 25 gig wavelengths. And then, because the handoff to the actual router is 10 electrical lanes, each at 10 gigabits per second, what you have here is a thing called a gearbox, which is converting these 4 lanes running at 25 gigs to 10 lanes running at 10 gigs. There's a lot of stuff, all inside quite a small optics module, so it's quite a sort of miracle of miniaturization, if you like. So it's quite good. Now, as far as the user's concerned, of course, they're not actually explicitly aware that there's 4 wavelengths on this fiber, because as far as they're concerned, they're just plugging in this optics module into the router, plugging in a normal single mode fiber pair into it, and so they don't have to know explicitly that there happen to be 4 wavelengths on the fiber. It's just the internal implementation. And so here's a picture of a 100 gig interface card, and so you can see the CFP module here. So it's got SC connectors. So the size of the module, I guess it's about 8 or 9 centimeters high and 1.5 centimeters wide. So this is accepted as the sort of way to implement these pluggable optics. So it's quite convenient. Oh, and I forgot to say, we actually demonstrated this card at the supercomputing show. So we demonstrated a prototype card in November 2009 at the annual supercomputing show. So this was running on our exhibition stand during the course of the exhibition, and people could see the packet counters and things like that to prove it was working. So I think that was the world's first public demonstration of a 100 gigabit Ethernet router interface card, which was good. Now, the other aspect is how to transport the 100 gigabit Ethernet signals through a long-distance DWDM system. And as I mentioned, if there are transponders on the DWDM equipment, then how to do it is really up to the DWDM vendor. It's nothing to do with the router, because they're decoupled from each other because of the presence of the transponder, which is converting from optical to electrical and then back to optical again. But nevertheless, it's interesting to see how they do it. And there are different approaches depending on the DWDM vendor. So some are planning on sending it on a single wavelength at 100 gigabits per second. Others, more as a sort of short-term, sort of interim step while they're developing this technology, are thinking of using 10 wavelengths, each running at 10 gigs. This is on the long-distance side of the DWDM system. And others thinking of using 340 gig wavelengths. So there's different approaches. But what I'll do is I'll look in more detail about how to do it at one wavelength, one single wavelength running at 100 gigs. Now I mentioned before that actually doing bit serial transmission at 100 gigabits per second is extremely difficult using on-off keying because of the problems with the transmitters and the receivers that I mentioned before. Now when you're going over long distances, another problem, or another couple of problems, is impairments due to the actual optical fiber, because the optical fiber isn't a passive medium. It's made of silicon dioxide, and that does interact with the light wave to some extent. And so one actual impairment is chromatic dispersion. And what that is different wavelengths travel at slightly different speeds in the optical fiber. If you've got a pulse of light, then inevitably it contains a spread of wavelengths, and so these travel at slightly different speeds, and so the pulse spreads out in time as it travels through the fiber. And so what that means is it merges into adjacent pulses, and so you can no longer distinguish between ones and zeros properly anymore. Now the killer thing about chromatic dispersion is that the impact of it goes as the square of the bit rate. So at 100 gigabits per second, it's actually 100 times worse than at 10 gigabits per second. And you can understand that because at 100 gigabits per second, this is if you're doing it on-off keying bit serial, because at 100 gigabits per second, the spectrum is 10 times wider, and you've got 10 times less space to spread, because the next bit is only 10 picoseconds away rather than 100 picoseconds away. So that's why it goes as the square of the bit rate. So that's a very serious impairment at 100 gigabits per second. The other one is polarization mode dispersion, because in the optical fiber, different polarizations travel at slightly different speeds because the fiber is not perfectly uniform, and that one is 10 times worse in terms of impact at 100 gigs compared to 10 gigs. So both of these are quite bad impairments, and so would seem to be insurmountable obstacles. Now the solution, in fact, as it turns out, is to use a higher order modulation format. So instead of doing just simple on-off keying, instead of just flashing the lights on and off, you use a higher order modulation format. Now these higher order modulation formats have been used in radio for decades. So for radio, it's nothing new. For optics, it's something that's very new. It's quite a revolution in the optics world. Now there's two really important consequences of using these higher order modulation formats. First of all, they're extremely resilient to chromatic dispersion and polarization mode dispersion. And so in field trials, people have shown that certain optical fiber, which was previously incapable of carrying 10 gigabit per second signals using on-off keying, was shown to be capable of carrying 100 gigabit per second signals using this higher order modulation scheme. The other aspect is that the spectral efficiency is much better. If you consider a system based on 10 gig wavelengths, then you've got a grid where the wavelengths are separated by 50 gigahertz. And so the spectral efficiency is only 0.2 bits per second per hertz. And again, if you're used to radio, you might be used to 5 or 6 or 7 bits per second per hertz. You might think this is a real waste of spectrum. If you're using these higher order modulation schemes, then you can get 2 bits per second per hertz, because you can still use the 50 gigahertz grid. You've got 100 gigabit per second wavelengths on each grid point, so that's 2 bits per second per hertz. So you've got a factor of 10 improvement in spectral efficiency. So I'll show you an example of one of these higher order modulation schemes. So this is quadrature phase shift keying, or QPSK. And so the idea is that you've got 4 possible phase states as shown on this phase diagram, and so that means that each state can carry 2 bits. So you've got 0, 0, or 0, 1, or 1, 1, or 1, 0, depending on what phase you're sending. And so you have a decoder at the receiving end, which is decoding these into the actual bits. And the other thing is that you can use polarization as an extra degree of freedom, and that's known as DP-QPSK, dual polarization QPSK. And with that, you're carrying 4 bits per symbol. So instead of sending 100 gigapulses per second, you're only sending 25 gigapulses per second, but each one's carrying 4 bits. And so that's the essence of these higher order modulation schemes. Now you might ask, why is a router vendor talking about these higher order modulation schemes because this is all happening in the DWDM system. So what's that got to do with the router, given that there's a transponder anyway on the DWDM system, which is providing decoupling between the router and the DWDM system? Well, the answer is, in future, it'd be interesting to actually put the long-distance laser directly onto the router interface card, so you don't have a transponder here. And so all this stuff of the fancy modulation format, the DP-QPSK, is actually happening on the router line card itself, and you're eliminating the transponder from the DWDM system. And so that implies that the router line card also needs to be able to do forward error correction and things like that, which you associated with long-distance DWDM systems. So that's more of a longer-term thing. In the first instance, we'll have the traditional grey interfaces for 100 gig products, but this is something that could be of interest for the future. So that brings me more or less to the end. Some interesting references. So the first one is the IEEE website, where you can see about all these different specs that have been talking about for the grey interface formats. Also, there's the CFP specifications and how these various CFP modules work. And finally, a data sheet which is talking about a 100 gigabit router interface product that we're planning on shipping quite soon. And so, just to conclude, really, we've been seeing very strong demand for the 100 gig Ethernet. As I mentioned near the beginning, we demonstrated prototypes at the supercomputing show in November of 2009. The next thing is field trials. So the next stage is going to field trials, which will happen in various places. Most of those haven't been announced. One of them, which is going to happen, has been announced, so you can read about that there. Other ones are being kept quiet, but then, once they've occurred, there'll be announcements about them, so watch out for those over the next few months. So that brings me to the end, so I'm happy to take any questions or comments, and thank you for your attention.